Okay. So again, just as a review, this first example is review from 9.1. We're using the letters in the word table, which means how many letters do we have? 6. And how many 4-letter words can we make? So that's telling me right now, this. All right. We don't seem all right. So, somebody want to tell me? 6 times 5 times 4 times 3. That gives us 360. The word must end in a T. So there's the restriction. I have to go to the last position of the word because it can only end in T, which means how many choices? 1. Okay, the T has now been used up. Now I can go back to the beginning. 5, 4, 3. And that gives me 60. The word must start and end in a vowel. So actually, I've got to go, I can go to this one and then this one, or I could go to this one, then this one. But I have to do these 2 positions first. So let's start here. It has to begin with a vowel. 2. I have used one of the vowels up here, haven't I? So 1 here. Right? It has to end, it has to begin and end in a vowel. So for this one, I could use an A or E, but then once I choose one of them, there's only one left for this position. Yeah. Now, the 2 vowels are gone out of the 6 letters. How many could go here? 4, then, good. 24 ways. Only consonants are used. Anybody want to ask it? It's not a vowel.
4.
4 times 3 times 2 times 1. You know what vowels are? The rest of the letters are called consonants. Okay, so that was, you guys seem to have a good handle on that. But what happens if some of the letters are the same? So for example, the letters from the word pool. Well, one would think how many 4-letter words you could make, you would go 4 times 3 times 2 times 1, right? But doesn't that count the O's twice? Like that's saying that pool can be one word. Like let's say you could have pool, where this is the first O, and this is the second O. And then you could have pool again, where this is the second O, and this is the first. Right? So, no, hang on. We're going to have to divide. I'm just explaining that right now. So obviously these are the same letters, or these are the same words. So that means that's going to happen a whole bunch of times, isn't it? Okay? So think of that when I do this. So if one would assume, okay, if all the letters were different, we'd go 4 times 3 times 2 times 1. Or 4, what's the shorthand? It's not 4 2. 4. Yeah, but what's the mathematical name? All right. Factorial. Okay. But 2 of the letters are the same, so we have to divide the arrangements in half, right? Because pool appeared twice, and loop would appear twice, and polo would appear twice, and lopo would appear twice, and opal would appear twice, okay, etc., etc., etc. So I've got twice as many as I need. So what do? I divide by 2. Technically, I divide by 2 factorial. Because how many different ways can I arrange 2 O's? 2 ways, right? Or 2 times 1. Like if you think about it, if I had O and O, I could put one of the O's in the first position, so I have 2 choices, and then there's only 1 choice for the other one. So it's 2 factorial. Because the O's can be arranged in 2 different ways. So we would say, and here's, it's good to use factorial notation. So this is if there were no repeating letters. Because 2 letters, or because a letter repeats, I have to divide it by 2 factorial. So that gives me 24 divided by 2, which is 12. What would happen if the word was oop or poo with 3 O's? How many ways could you arrange 3 O's? Not 3 ways. Think of how many ways you can arrange 3 O's. 3 times 2 times 1, 6 ways. Okay, I got, okay. I don't think that. Okay. So the number of letters that are repeating matters, and sometimes there may be more than 1 letter that repeats. When that happens, you just follow this formula. If we've got a set of n, say, letters, objects, and A of those n are identical, and perhaps B of another kind are identical, and C of a third kind are identical, we can arrange them in n factorial over A factorial times B factorial times C factorial. This will make more sense when we do a couple of examples here. So first of all, get the number of letters in the word or the number of digits in the number. It's not say words. How many letters? So if all the letters were different, that would be the arrangements, right? 5 times 4 times 3 times 2 times 1. But all the letters are not different. So I have to divide those repeats away. 3 factorial. Perfect. Because there's 3 E's. 3 E's can be arranged 3 times 2 times 1 way, 6 ways, which I have to divide away. So 5 factorial is, what, 120 divided 6? 20? Or just be 5 times 4. Aardvark. So we got 8 to start with if they were all different. But now I have to divide away the repeats, and this time more than 1 letter repeats. What about the A's? So 3 factorial times any other letters that repeat. No, the R's, there's only two of them. No, you can't. 3 factorial plus 2 factorial is not 5 factorial. Good question. Okay, so these are the A's, these are the R's. I have to divide away those repeats. And when I do 8 factorial divide that, I get 3360. You should have a factorial function on your calculator. Okay. On the graphing calculator, you actually have to go to math to find it on the graphing calculator. So like if you have your graphing calculator on and if you hit math, and then this is part of probability. So you have to scroll over to PRB and you should see number 4. Okay. So to find 8 factorial, punch 8. And then for those of you that have a graphing, go math, scroll over to PRB, scroll down to the exclamation mark, and then hit equals, and you've got your answer. But then we have to divide that by these. Yes. Okay. If you don't have a graphing calculator, on some, I think on yours, you would find it in PRB. There should be a button that says PRB. Yes. Yeah, and then you just scroll over and choose that.
Oh.
Yeah.
Wait, which one?
What's that? Did you find it on that one? Okay, hang on. Let's look at a couple of different examples. Oh, no, that's not right. How many digits, 5-digit numbers can be made from these digits? So if there was no repetition of digits, 5 factorial, but I have to divide by any repeating ones, factorial, how many times they repeat? Times 2 factorial times 2 factorial, because this accounts for the 4s, this accounts for the 6s repeating. When you do that, you will get 30. Okay. How many possible answer keys are there on a 10-question true-false test if 5 of the answers are true and 5 of the answers are false? What do you think? If they were all different letters, let's say that in true-false question, there are 10 different ways to answer. Okay? Like slightly true, slightly more true, slightly more than that true, I don't know, whatever. Okay? How many different ways? How would you find it? 10 factorial. But that's not the case. 5 truths, there's 5 truths, and there's 5 falses. 5 factorial times 5 factorial. Okay? So this would be the truths or the falses, and this would be the other one. And this would be if there was 10 different ways to answer a true false, which is obviously silly, but. Just want to make sure I was recording.
252.
Yep. This one. Paths you follow from A to B in a 4x6 rectangular grid if you can only move up and to the right? Well, okay, so let's figure out how many moves are there to get from A to B. So let's just take one example. So okay, let's say we go up. That's 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I did it in 10 moves, right? Isn't that going to be the same no matter what? So like if I started A and if I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same thing. It's always 10. Okay? So that means 10 factorial. Now, we're going to have repeats though, right? We're going to repeat how many times we go up and how many times we go right. Not quite. You got it reversed. What's the maximum up I can go? I can only go 4 up maximum. There can only be 4 U's. And there can be a maximum of 6 R's. So that's how you would do it. So these are the ups. And these are the rights. Because if you look at the grid, no matter what path I choose, it's always going to contain 4 ups and 6 rights, right? Like this red one, it's got 1, 2, 3, 4 ups, 1, 2, 3, 4, 5, 6 rights. Every one of them will contain them. 210? That is correct. Okay, so that's permutations with repeating objects. One more type with permutations. One more kind of restriction. Okay. We've got 5. This is the one, this is very similar to the one we had in exercise 9.1, except this time it's not 8 people, it's 5 people and 5 seats. So how many ways can they sit? How many arrangements can I make if there's no restrictions? What would be? How many people can I choose from here? 5, then 4, then 3, then 2, then 1. So remember, I mean, you could do this, write it out like that, or you could do, not every question works out to nice like this, right? I mean, if you put 5 factorial, that's still right. If you didn't write out the long way, that's fine. So this is 120. Okay, this is where it gets a little interesting. A and B have to sit beside each other. So there's still 5 positions. But what we do in a situation like this, when these two have to sit beside each other, treat them like one position. And I'm just going to put them on the end. I could have put them on the beginning. So I'm going to say A and B have to be in there. If you think about it, if A and B have to stay together, think of them as one. Doesn't that mean that I actually have only 4 to choose from now? Right? I can choose C, D, E, but A, B have to be together. So it's actually going to be 4 times 3 times 2 times 1. And it doesn't matter if I put these guys here. It's still 4 times 3 times 2 times 1. No, there's 5 places, but A and B take up 2 of them. No, because Hang on a sec. Okay. Appreciate the excitement. So it's going to be 4 factorial. Well, 4 times 3 times 2 times 1. Okay, you can if you want. But how many different ways can I arrange A and B within their little two-seater group? 2 ways, right? Because A or B could go here, and then the other one goes there. So inside this group, there's 2 factorial ways, which I have to multiply this by. So it has to be 24 times 2. Well, if you take out the factorials, it's 24 times 2, which is 48 ways. If 3 of them had to sit together, like let's say, I'll just do that as an example. If 3 of them had to sit together, now you got to block off a group of 3, which means there's only 3 positions, right? So there's 4 possibilities here, right? Sorry, 3 possibilities there. Yeah, 3 possibilities. Let's say A, B, and C have to be together. They can't be more than 1 apart from each other, or something like that. Okay. So that means C or D could go there, or this group, and then 2, then 1. But how many ways can I arrange the 3 within each other? 6 ways. 3 times 2 times 1. So this would be 3 factorial times 3 factorial. Anyway. This you got to think. Use the previous question. The hint I will give you, use the previous answers. A and B have to be apart to hit each other. Another hint, I don't have to use this. I've got the numbers I need. I don't need factorials because I've got the answers I need from the previous 2. How many ways can they all sit together if there's no restrictions? 48 of those ways is if A and B sit beside each other. If they can't sit beside each other, it's 120 minus 48. Which gives us 72. Because this is when it doesn't matter if they sit beside each other or not. This is they have to sit beside each other. So these must be, the remaining must be, they don't sit beside each other. A and B must sit together, so do C and D. Well, I still have 5 positions. But now I have to take 2 of the seats for A and B, right? And then I have to take another 2 of the seats for C and D. So let's say we're going to put A and B here. And we're going to put C and D here. Well, how many different ways are there overall if I need this as a group and this as a group? 3 times 2 times 1. Or 3 factorial. Or 3 times 2 times 1, doesn't matter. Okay? Because I've taken 4 of the seats and made them into 2 positions. Right? Now, within each one, I have to multiply by the number of arrangements I can make within. How many can I make within here? 2 or 2 factorial. How many can I make within here? 2 factorial again. So that's what I have to multiply that by. So it's basically going to be 6 times 2 times 2. And I believe you get 24. So that's kind of another permutation problem, is certain objects have to be beside each other. Usually it's people. Let's do one more like that. We got 4 married couples. They sit on a bench. Obviously, it's a bench big enough for 8 people because it's 4 couples. But the spouses insist on sitting side by side. Well, there's 8 positions. I have to pair this off for one of the couples, this off for another couple, this off for another couple, and that off for the 4th couple because they sit beside each other. So how many, when I do it overall, how many do I have now? 4 positions, right? 4 times 3 times 2 times 1. That's or 4 factorial. But within each married couple, they can sit 2 factorial ways. So I got to go times 2 factorial, times 2 factorial, times 2 factorial, times 2 factorial. Because this married couple can sit in 2 different ways. 2 factorial, same with this one, same with this one, same with this one. So 24 times 16, I believe. Should get 384. Okay. That's permutations. The next thing we talk about on Friday is combinations. So for Monday, you should really have exercise 9.1 done. I suggest try and do at least half of 9.2 for Friday, at least the questions that are on permutations, okay? Before I let you go, so